The topic of my tutorial is post-dynamic nuclear polarization. And so in post-dynamic nuclear polarization, that's interesting. This is being slow. So in post-dynamic nuclear polarization, just like in many other forms of DNP, you start by doping your NMR sample with a suitable polarizing agent. And in our case, or a test system that has become quite our favorite, the polarizing agent is the organic radical tritol. And we typically dope it into a frozen mixture of glycerol and water that's partially deuterated and also known as DNP juice. What we do then is we apply a microwave pulse sequence, and that will induce a transfer of electron spin polarization to a nearby proton. Depending on the sequence, this can take from a few hundred to a few microseconds. We then turn the microwave pulse sequence off. We stop applying the microwave pulse sequence. And during this time, we allow the electron spins to return to thermal equilibrium. We allow them to go back to relax. And this typically happens on a time scale of a millisecond. So the waiting time is typically about a millisecond. And during this time, proton-proton spin diffusion makes sure that the magnetization that we've just transferred spreads into the sample. This is a slow process, and it typically happens on a time scale of seconds. We then apply our microwave pulse sequence again. We induce another transfer of electron spin polarization to a nearby proton. We stop applying the microwave pulse sequence. We give the electron spins again time to relax, to go back to thermal equilibrium. And meanwhile, proton-proton spin diffusions continues to spread the magnetization into the sample. Now, typically, to build up dynamic nuclear polarization of all the proton spins, of the bulk proton spins, we have to repeat this process thousands of times until they're all dynamically polarized. And then we do one NMR experiment. And if we've done everything correctly, we will see that the sensitivity of our NMR experiment, in this case, a proton NMR experiment, is strongly enhanced. So why are we interested in doing DNP in this way? So instead of what's common in current MAS DNP, we don't apply the microwaves continuously, but instead we choose we find a clever pulse sequence to do tech transfer. And in fact, what we envision is that post-MAS DNP could be something of a version 2.0 of the current MAS DNP. Now, one reason that we think this is a good idea is that we would expect to have an improved efficiency in the electron-proton polarization transfer. So you can think of this polarization transfer as an optimal control problem. And what you see here in this slide on the right is a figure from an introductory course on optimal control. And so the task here is to have a particle that's moving at a certain velocity, to bring it to rest at the origin of this figure in the shortest possible time. And contrary to what you might expect, the trajectory that the particle needs to follow is not a straight line, but instead you can show that it has to follow one of these parabolic trajectories. So with this in mind, it's not very likely that the most efficient way to induce an electron-proton polarization transfer is just plain old continuous wave irradiation. There's probably a pulse sequence out there that's much more efficient and is doing a much better job. So if we would apply such a sequence, this would allow us to reduce the average microwave power that we are applying during our DNP experiment, and this would mitigate sample heating, which can be a problem at the higher fields and frequencies in the MAS DNP experiment. Also, it's reasonable to expect that as DNP evolves from continuous wave to pulsed, we will devise new experiments which will give access to new information. So we would be able to answer new and different questions from material science, structural biology, and chemistry in general. Another important reason that we think that pulse DNP is interesting to investigate is that it would give us more flexibility in the excitation. So here, also on the slide on the right, you see the EPR spectrum of manganese doped in lithium titanium oxide. You see here the typical 6 lines of manganese. And so manganese can be used as a polarizing agent in DNP, but from this spectrum, it's immediately clear that if you just use monochromatic continuous microwave irradiation, you cannot excite such a spectrum efficiently. However, you could think of devising a pulse sequence that can. Another place where flexibility in excitation is important is if you need a rapid transfer from a short-lived photoexcited triplet state. For example, the photoexcited triplet state of pentacene as it is used in a triplet DNP experiment. And finally, it's reasonable to expect that post-DNP will be more effective over a larger temperature range compared to CW DNP, as we don't depend on saturation, and therefore the efficiency is less dependent on relaxation properties. So now there in this series of tutorials, there are already several tutorials on MAS DNP. So I don't want to go into the technical and aspects of that and the tremendous development that has taken place over the last decades. I just want to highlight one part of the instrumentation that's actually crucial in getting this to work, in getting high field MAS DNP to work. And that is the microwave source. So the microwave source is a gyrotron. And here you see a picture of the very first high-field MAS DNP spectrometer that was built at MIT. The gyrotron here was producing 140 gigahertz high power, so high-frequency microwave radiation continuously at a power of 10 to 20 watts. And also in the modern commercial MAS DNP instruments, the gyrotron is the source of the microwave radiation. So a gyrotron is a special kind of vacuum electronic device in which electrons are accelerated in a magnetic field. And so you see that here in this technical drawing, and actually in the magnetic field, they do this, or they undergo this sort of spiraling trajectory. The interaction of the electron beam with a resonance structure is then responsible for the generation of the high power microwaves. So why do we need this very complex and expensive device to generate the microwaves? Well, there's actually fundamental physics, or the fundamental physics that is the reason for that. So when you go to the fields and frequencies that I would call that would result in high resolution MAS DNP, maybe starting at a magnetic field of 9.4 Tesla and going up, the corresponding microwave radiation that you need starts essentially at 263 gigahertz. The wavelength there is about 1 millimeter. And so at this frequencies and wavelengths, you're starting to enter the terahertz gap. And that's a region of the electromagnetic spectrum where it's just, for physical reasons, very difficult to generate high power radiation. The main reason is you cannot use solid state devices. So as a rule of thumb, power times frequency square is constant. And even with the best materials today, at 100 gigahertz, you can generate a few watts. But that at a 200 gigahertz, that already puts you down to 200 milliwatts. And it's physically impossible to generate more power with solid state devices. So what you could do instead is switch to vacuum devices. And one category that comes to mind are the so-called slow wave devices, like the klystron, the magnetron, and also the traveling wave tube. And some of you may know that it's possible to use a klystron as a source for MAS DNP at 263 gigahertz. However, these devices have a disadvantage, which is that they rely on a fundamental mode resonance structure. So 263 gigahertz, this is a very fine grating that matches with the wavelength, which is about 1 millimeter. So it's a very fine structure, and that is even intrinsically incompatible with generating over a long period of time high power irradiation. And so what you typically see is that the quality of this resonance structure degrades and the power output goes down as you use the device more often. So the better solution is to go to a different type of vacuum device, so-called fast wave device. And a gyrotron is one of those devices. So a gyrotron it can be overmoded, and therefore it can produce high power at small wavelengths. So what we would now need to do pulse MAS DNP at high fields and frequencies is such a gyrotron, or a fast wave vacuum device to generate microwave pulses. So instead of doing the casual continuous wave irradiation at 10 to 20 watts, we want these high power coherent pulses, where the average power that you apply to the sample would typically still be less than what you apply, what you apply in the continuous fashion. Now the problem is that it's really hard to make these coherent high power pulses with a fast wave vacuum device. And so for that reason, for the moment, pulse DNP experiments are only possible at low fields and frequencies. And so the result of the experiments that I'm going to show you will be at the microwave frequency 9.7 gigahertz, also called X-band, and 34 gigahertz, also called Q-band. That corresponds to magnetic fields of 1.2 Tesla and 0.34 Tesla. Now, this is the region where post-DNP experiments are currently possible. So we nevertheless decided not to let that deter us. Post-DNP was, up to a few years ago, an idea that was explored very little. So we said, okay, let's go and design these post sequences. Let's go and do experiments. We will certainly learn something. So we started with what you might know as the original DNP post sequence. It's called novel, which stands for nuclear spin orientation via electron spin locking. And here you see a scheme of that DNP pulse sequence, and it's the DNP block. We essentially apply spin lock to, with the microwave irradiation, we apply spin lock to the electron spin. So we apply 90-degree pulse, we change the phase by 90 degrees, and then during a time that we call the contact time, we induce a transfer of electron spin, longitudinal magnetization. Now we typically only transfer when we meet the matching condition of the DNP pulse sequence. And in the case of on-resonance novel, the matching condition says that the electron Rabi frequency or nutation frequency that we generate with our microwave irradiation has to match with the proton Larmor frequency. So the gyromagnetic ratio minus the gyromagnetic ratio of the electron spins times the B1 field, so the magnetic field component of the microwave irradiation has to match with the product of the gyromagnetic ratio of the nuclear spins, typically the protons, and B0, so the strength of the external magnetic field that we apply. Now, what we found quickly is that at low fields and frequencies, so for example, X-band, 0.34 Tesla, the novel sequence works really well with the organic radical tritol in this frozen glassy matrix of glycerol and water. We easily could get enhancements and enhancement factors in the sensitivity of more than 200. And so what we could then show is that this DNP pulse sequence novel works really well at low fields in a chemical system that is compatible with biomolecular MAS DNP. The novel sequence itself, however, is not compatible with doing MAS DNP at high fields and frequencies. And that's because of a problem that you can already see from the matching condition. So the electron nutation frequency is minus the gyromagnetic ratio of the electron spins times the B1 component of the microwave irradiation. And that B1 component is proportional to the square root of the microwave power that we apply. So at low fields, at 1.2 Tesla, it's easy to match the proton Larmor frequency of 15 megahertz. However, when you go up in field, say the Q-band, 1.2 Tesla, matching 51 megahertz already becomes technically somewhat challenging. Going to 9.4 Tesla, 400 megahertz, 18.8 Tesla, matching at 800 megahertz proton Larmor frequency becomes technically very challenging. So if you come with a novel sequence and you go talk to your microwave engineer, then he say, can you build me a source that can do that? Because I would like to do this experiment. It's not very likely that you'll get a positive response from him or her. Now, fortunately, we found also pretty quickly that things are not as bad as they seem. So in a project that I did together with Sheetal Jain, who also gave a tutorial in this series some time ago, we could show that you don't have to quite match the on-resonance novel condition. There is actually a more general matching condition where you match the effective field, which is really the vectorial sum of omega-1s, so the electron, the Rabi frequency, and the microwave resonance offset to the proton Larmor frequency. So when you do that, you can compensate a low nutation frequency by going slightly off resonance. And in experiments at X-band, we could show that this works pretty well down to lower nutation frequency. Now, what was also an important thing that came out of the experiments that we did is that we realized that you can derive the matching condition for novel, and also the polarization times, you can derive them theoretically using the average Hamiltonian theory. And that's a theoretical tool that's commonly used in solid-state NMR and magic angle spinning NMR to design recoupling and decoupling pulse sequences. Now, this is something that Shito also discussed in his tutorial. I don't want to go into that today. I just want to mention that we realized that from this experiment, and it was then actually Kong Tan who then took this to a higher level when he developed or designed the top DNP pulse sequence. So top stands for time optimized pulse DNP. And instead of applying a spin lock like we did in the novel sequence, we now apply a pulse train. So this pulse sequence just consists of a pulse, delay, pulse, delay. Under the influence of this pulse train, the electron spins will undergo a complex trajectory. So you see that in this figure. I've plotted what happens to the -Z magnetization when we start to apply the top DNP pulse sequence. So you'll see this nice curly flowery pattern. And this trajectory will actually have two basic frequencies in it. And the first one is the modulation frequency, which is 2 pi over Tm, the modulation length or time. So that's the length of one block in the pulse sequence. And then there is another frequency, the effective frequency, which is the effective flip angle, again, per block of the pulse sequence. So with every block, apart from the curl that we do, we also have an effective flip angle, and that causes another nutation around the direction of this effective frequency, which is indicated here by the red line in this pattern. So you can now show that if I take a multiple of the modulation frequency, plus or minus this effective frequency, and I match that to my proton Larmor frequency, I will also have a transfer of polarization from the electron spins to the proton spins. Now, this is a very much nicer matching condition than the one for a novel, especially because K can be a multiple. It can be 1, 2, 3, 4. And whereas the effective frequency still depends on the amount of microwave power that you have available, you're now much more flexible in meeting this high Larmor frequency. As it turns out, it's now quite straightforward to do these experiments at 1.2 Tesla, 34 gigahertz or Q-band. And now this is now a starting point for a conversation with a microwave engineer and say, okay, can you build me a source for 9.4 Tesla, so 263 gigahertz? As it turns out, this principle is quite general. And so in recent years, my group was able to add 2 sequences that follow this same high field friendly matching condition. The first one was the X inverse X or XIX DNP sequence, where we simply take an X pulse, change the phase by 180 degrees, apply this pulse, a minus X pulse, X minus X, and we repeat it that way. And as a generalization, we could also show that the 2-pulse phase modulation or TPPM sequence can also be used for DNP. So here the phase change between the 2 pulses can have any value. What's intriguing about this is that these 2 sequences are also used in magic angle spinning NMR for decoupling. So these 2 sequences we could introduce in 2022 and 2023 together with my former postdoc, Paul. Meanwhile, there's yet another member of this family called BEAM, broadband excitation by amplitude modulation. BEAM relies also on an X and a minus X pulse, but now the pulses don't have the same length. And as I'll show later in my talk, for that reason, this pulse sequence needs a 90-degree preparation pulse, very much like the novel for the spin. Okay, so how do these sequences work? So the spin Hamiltonian that we need to describe these sequences is actually fairly straightforward. So we can just consider an electron coupled to a proton. And so I've already performed here a transformation to the electron rotating frame, but I'm still in the lab frame. So I have here an electron Zeeman term, and this capital omega is my microwave resonance offset. I have a nuclear Zeeman term. I have microwave irradiation, in this case along the X direction, which can be time dependent. After all, we're applying a pulse sequence. And then we have the coupling between the electron and the proton. That can either be dipolar coupling or the Fermi contact interaction. So the dipolar coupling and Fermi contact give rise to this term, A, that's just a constant, SZIZ. And another term, B, again, just a constant, SZIX. And if you've studied NMR to some extent, you're probably not surprised by the presence of this term, STIZ. That's the term we always need in the high field limit and the secular approximation to describe the heteronuclear dipolar coupling. However, maybe you're surprised by this term. This term is also called the pseudo-secular term. And if you consider heteronuclear dipolar coupling between two nuclei, say a proton or a carbon, you can neglect this term. However, in the case of interaction between an electron and proton, it's not negligible. And the reason for that is that the gyromagnetic ratio of the electron spins is 658 times, so much larger than that of the proton. And therefore, yeah, you cannot neglect these terms. And it's a very different situation that you have when you compare the gyromagnetic ratios of a proton and a carbon. But the difference, or the ratio of the ratios, is just a factor of 4. Now, as we'll see in a bit, this term is actually responsible for DNP. So we consider this spin system, and also for now, we're just going to consider a single electron-proton transfer in our description. Okay, so we have our spin Hamiltonian, and now we would like to investigate the time evolution of our spin system under the influence of this Hamiltonian. Now, for that, we need the Liouville-von Neumann equation. That's the equation of motion. And it says that the derivative with respect to time of the state of our spin system, given here by the density operator rho, is equal to minus I times the commutator of Hamiltonian and the state of our spin system, the density operator rho. So the commutator here, that's just h rho minus rho h. Now, this equation in general has a very complex solution, or it's not so obvious what the solution of this differential equation should be. However, if the Hamiltonian is time independent, the solution is quite straightforward. So I can now take the starting state of my spin system at time 0, and I can apply a unitary transformation, which I'm denoting here as U, to get the state of my spin system at time t. And this unitary transformation is actually given by the exponent, or e to the power minus IH, the Hamiltonian t. And we typically call this a propagator because it propagates the state of the spin system forward in time. Now, if we now have a pulse DNP experiment, we can describe this as a sequence of time intervals governed by different time-independent Hamiltonians. So maybe for our first pulse U1, for the second pulse U2, then for a delay U3, and so on. So we can use this principle to do a numerical investigation, where we simply calculate numerically our propagators for time intervals during which the Hamiltonian is constant or is assumed to be constant. And nowadays, this is actually quite straightforward to do because we have powerful computers, and also there are several user-friendly and very advanced software packages available that will allow you to do that. However, it's still interesting and relevant to also look for an analytical investigation. And so what we typically, because this gives you typically insight into how a pulse sequence works, and therefore it's important to do this if you want to design a pulse sequence. So what you typically do here is you use some form of perturbation theory to find an effective time-independent Hamiltonian that describes the evolution of your spin system. After you've applied this evolution, you can just retrieve the expectation value of your observable of interest. So in our case, that's typically IZ, the longitudinal expectation value of IZ, the longitudinal magnetization of our nuclear spins at any time by taking the trace of the product of the state of my spin system with the operator, the observable that I'm interested in. Okay, so how do I now go about in designing a DNP pulse sequence? Now, the first thing is, or the first step is that you split the Hamiltonian into 2 parts. A large part that contains the large terms, so in our case, the electron and nuclear Zeeman terms, and also the strong microwave radiation in our case. The other part will contain the small terms that describe the interaction that is going to be responsible for our transfer of polarization. In our case, that's the dipolar coupling between the electron and the proton. We then transform to an interaction frame. And so that this transformation then looks like this. So I take the state of my spin system, And I apply a unitary transformation, but notice here that now there's no minus here, the minus is here instead. So actually we're, and that's also the road runner is going in the opposite direction. So I'm applying a transformation to remove the large part of the Hamiltonian, so H0. And I use the state of my spin system in this to indicate that this is the state of my spin system in the interaction frame. I use this tilde. But the Liouville-von Neumann equation still applies also in the interaction frame. And if I now calculate or I look at the shape of my Hamiltonian, I'll see that it looks different. It has transformed in the interaction frame following this equation. So this is just my original Hamiltonian where I have applied my unitary transformation. And this term just comes from the product rule. But when you fill this in, you see that this transformation has exactly the effect that we want, because it removes now the large part of our Hamiltonian that we're anyway not interested in. We would like to see the evolution of the system under our interaction, under the influence of our dipolar coupling. So this is indeed what remains. H1, it's just now modulated by the large term in the Hamiltonian, H0. So I'm indicating that with H tilde. The norm, however, of this Hamiltonian in the interaction frame is small. Propagation is therefore slow, and hence I can typically use some perturbation theory. My series expansion that I use in my perturbation theory is likely to converge quickly. So I can use this series expansion, my perturbation theory, to find an effective time-independent Hamiltonian that describes now the propagation of my spin system in this interaction frame. And that's what you show here. And so the bar indicates now this effective Hamiltonian. What's important, that if I want to calculate the evolution of my spin system, that I shouldn't forget afterwards to transform back. Now, when you design your pulse sequence, this is typically an iterative process that you go through. And what you do is you choose your irradiation and your conditions of your experiment such that the dipolar coupling is preserved in this effective Hamiltonian. And when you manage to preserve it sufficiently, you'll see that the polarization will be transferred as the system evolves. Okay, so now let's go back to the spin Hamiltonian that we use for pulse DNP. So as I already mentioned, the electron Zeeman term, the nuclear Zeeman term, and the microwave irradiation go together in the large part, H0, and the interaction between the electron and the proton, they go into the small part, H1. But I can already mention that this part, the secular term, will have no effect, and so we will only focus on the pseudo-secular term, so the term B, SZ, IX. So our aim is now, starting with our electron spin in thermal equilibrium, where our magnetization is essentially that of the electron spin. So rho 0 is minus SZ. That we find an effective Hamiltonian that transforms minus SZ into IZ. So we're transforming our longitudinal electron spin magnetization into longitudinal nuclear spin magnetization. Now, it turns out that in order to do that, we need to preserve these double quantum and zero quantum terms, which will do the DNP in the effective Hamiltonian. And we can do that by irradiating on the electron spins, but not on the proton spin. So it's actually the pseudo-secular term that will be responsible for that, or that will lead to these terms when you apply irradiation on the electrons, but not on the proton spin. Okay, so we have a general strategy. So, but how do we choose or find this suitable interaction frame that we need to get our perturbation or a series expansion for the perturbation theory to converge quickly? Now, if you've studied NMR to some extent, you've probably already encountered the tilted rotating frame. So what a tilted rotating frame is, it's an interaction frame. And what it does, it removes essentially the effect of continuous radio wave or microwave irradiation. And so here you can see how that works. So let's say we apply our radiation along the X direction. So our omega 1 is minus gamma of the nuclear or electron spins times V1, and we apply it along the X direction. Now, the consequence of that is that the magnetization of, let's say, our nuclear spins will start to rotate in the ZY plane. And so what you now see that in order to move if we want to transform to a frame where we don't no longer have this motion. We want the magnetization vector to stand still in our interaction frame. And so what it means, we need to choose our frame that rotates around the x-axis, but now in the opposite direction, so that my magnetization, even though I apply the microwave radiation, still stands still. And so what that means is I need to tilt my frame by 90 degrees so that my z-axis aligns with x and I rotate. So that's the tilted rotating frame. I can do the same thing, not for on resonance, but for off resonance irradiation. So now there is the precession around, not around the x-axis, but around the effective, omega effective, which is no longer pointing along the x-axis, but somewhere in between the x and z plane. And so what that now means, I don't need to tilt the full 90 degrees, but I just need to tilt by this angle theta to remove the effect of my off-resonance microwave radiation. Now, in our pulse sequences, the situation is a little bit more complex. So we don't apply the microwave radiation continuously, but we have some pulse sequence. Nevertheless, the principle for choosing the interaction frame and also in particular the tilting is really quite the same. So what we do is we remove the modulations that come from the microwave pulse sequence and the nuclear Larmor frequency. So the nuclear Larmor frequency, that's easy. That's similar transformation that unitary transformation that you've seen before. The one to deal with the microwave pulse sequence is more complicated. And so this error means that this is a time-ordered exponential. And we essentially need that because z and sx here don't commute. And of course, we need it time-ordered because omega 1 is now time-dependent. We are applying a pulse sequence after. So this is now the transformation that we need to apply to get rid of the modulations by the microwave pulse sequence. And this gives us now a Hamiltonian in a frame that I started calling the modulating frame. So this is very similar to the expression that you've seen before, the Hamiltonian in my interaction frame, so indicating here with the tilde. And so this transformation has again the effect we want. It removes the large part. So that's the electron Zeeman term, the nuclear Zeeman term, and also the effect of the microwave radiation. So when I work this out, what will remain behind was this secular term and also the pseudo-secular term, where now the z operator is now rotating in the xy, is now rotating in, sorry, the ix operator is now rotating in the xy plane under the influence of my rotation. And here, for convenience, I've rewritten that in terms of the raising and lowering operator. Now, as z will take a more complex form, but what's important is that we're not there yet. We haven't reached the final proper interaction frame, and that's because we have not yet applied the tilt. So we also still need to apply the tilt. And just like in the tilted rotating frame, we're going to tilt the frame such that the z-axis now aligns with omega effective. Now, this omega effective is not the vectorial sum of omega 1 and capital omega, the resonance offset, but this is the effective frequency that I already indicated when I first described the trajectory of the top DNP sequence. So it's actually this effective, it's the effective flip angle divided by the length of each block of the pulse sequence. And its direction is indicated by this red line here. So in this case of the top DNP sequence, we don't need to tilt the frame very far. However, there are also other conditions for the top DNP sequence, especially close to resonance, where this tilt angle is larger, and it's more important that you do also perform this tilt in order to get your series expansion to converge quickly and to properly describe the sequence in this way. So now that we found the actual interaction frame, what we're interested in is the trajectory of the SZ operator in this frame. And it will take on a general form, which I've written down here. And I'm indicating this SC with prime here to indicate that I'm now in the tilted interaction frame. So the tilde is also still there. So we'll have a general form where the components as x, as y, and as z. And again, I've conveniently rewritten that in terms of the raising and lowering operators. And they now also have time-dependent constants in front of them. So that's just how I'm describing the trajectory of SZ in interaction frame. And it's now not difficult to show that these time-dependent coefficients can be written as double mode Fourier series, with two basic frequencies, the effective frequency and the modulation frequency. Now what we now want in the end is to find the Fourier coefficients A plus and A minus, which tell us the contributions of these two frequencies. And as you'll see, they'll end up in the effective Hamiltonian, and they're important later on. Okay, so in general, in this interaction frame, the Hamiltonian can be written as a Fourier series with three basic frequencies. The effective frequency, the modulation frequency, and of course, the proton-Larmor frequency. Now, this description, this general description, is actually similar to what was encountered in the description of recoupling and decoupling sequences in magic angle spinning NMR, and particularly in the description of the TPPM heteronuclear decoupling sequences, where the rotor frequency is actually plays the same role as the proton-Larmor frequency in our case. Note, however, that the origin of this term is different. Whereas the oscillation with the rotor frequency comes from the intrinsic time dependence of the Hamiltonian, the rotation here, the modulation with the Larmor frequency, comes from our frame transformation. Okay, so we have our Hamiltonian in as a Fourier series with three basic frequencies. And now what we can do is we can follow what was developed by Ernst and co-workers, the operator-based triple mode Floquet theory, which tells us that at the matching condition, the effective Hamiltonian takes a form of a complex series expansion, but fortunately, the zeroth order term are just these Fourier coefficients, and those we already know. Luckily, we do not need to worry about the second order because there the terms become a lot more complicated. So it's now quite easy to show that at the double and zero quantum condition, so double and zero meaning that L and N coefficients have the same or opposite sign, the effective Hamiltonian is given, and now I'm just looking at the pseudo-secular term, so the constant B will have these simple forms. And now what you see here is that we have the double and zero quantum operators, which will do the DNP for us. They're determined by the strength of the electron-proton dipolar coupling and scaled with this Fourier coefficient that we get from the trajectory of SZ in the interaction frame. So we can find them from a double mode Fourier analysis, so looking for the contributions of the effective frequency and the modulation frequency in the trajectory of SZ in the interaction frame. So now that we have our effective Hamiltonian, we can do the evolution, starting in thermal equilibrium, so ρ0 is minus SZ, and read out the expectation value of IZ, which is what we're interested in by taking the product of the trace state of our spin system and IZ. So that's this complex expression, because remember, we still use the frame transformation. So when you work out the math, you get these very simple expressions for the magnetization, the longitudinal magnetization of I, of the nuclear spins. You get a periodic transformation of minus SZ into IZ. So I plotted both functions here for you at the double quantum. An expectation value of IZ oscillates between 0, -1, 0, -1. And at the zero quantum, it oscillates between 0 and 1, 0 and 1. The frequency of this oscillation is now determined by B, so the strength of the pseudo-secular term, the strength of the dipolar coupling between the electron and the proton, and the square root of these Fourier coefficients A plus and A minus. So this square root altogether scales the dipolar coupling. So if it is smaller, the oscillation will be smaller, and this means that the transfer of the magnetization will be smaller. And so this is this factor. I'm going to call it K. In the next slide, is typically called the scaling factor. So what we now, knowing this, what we now did is we analyzed for 3 of the sequences that we investigated, top DNP, XIX, and TPPM DNP. We analyzed the trajectory of SZ in the interaction frame, and we calculated the scaling factor of the dipolar coupling. So for top DNP, we found that 0.1. For XIX, we found it to be 0.21. And for TPPM, we found it to be 0.34. And here you see the consequence of that. So this is still the periodic transformation of minus SZ into IZ. However, I've done here powder averaging. So I'm taking into account the anisotropy of the dipolar interaction. And that what you see is that there is a transfer of magnetization. Well, these oscillations remain as a remnant of the dipolar averaging. So what you see now is, as expected, that the transfer is the slowest for top DMP, followed by XIX, and the fastest transfer is for the TPPM sequence, in agreement with the analysis of the trajectory that we impose with the three different sequences. So the solid line here is now what we calculated following our perturbation theory approach. And you see here also a dashed line, and that was actually done using numerical simulations. And you see that the two approaches match really very well, which is also a confirmation that we did our theoretical treatment correctly. So you may have noticed that in this periodic transformation, or the formation of IZ and the expectation value of IZ, that in this oscillation there was also a prefactor. And this prefactor actually comes from the fact that we do the transformation in this interaction frame, and we have tilted the frame. So this product here is essentially the scalar projection of rho 0 minus a z onto the direction of direction omega effective onto the direction of this vector. Now, in the case of the top DMP, XIX, and TPPM sequence, omega effective, again indicated by the red line, you see that we don't have to tilt very far. These omega effective is pretty much along the z-axis. So that's good news, because that means that this projection here is very close to 1, and we can do the transfer pretty much completely. However, when you now look at the beam sequence, you see that the direction of omega effective is pretty much, it's almost perpendicular to the z-axis. It's here pointing along the minus x, or pretty much pointing along the minus x-axis. So if we would now calculate this projection, you'll see that you get to a value that's close to 0. And so with this trajectory, this means you would not be able to transfer any magnetization at all. Luckily, there is a solution to that. And so what you can do is, instead of starting with your magnetization along minus z, you can, before you start your sequence, you can apply a 90-degree pulse, flick the magnetization into the xy plane. In this case, along, make sure that it ends up along x with a 90-degree preparation pulse. And so now you see why the beam sequence needs this 90-degree preparation pulse in order to start the transfer of polarization. Okay, that's a lot of talking and a lot of theorizing about how these sequences work. Let's have a look at some experiments. So what I'll show you will be experiments at 1.2 Tesla. That's at Q-band, 34 gigahertz. And essentially what we did is we took a commercial pulse DPR spectrometer, we extended it and transformed it into a pulse DMP instrument. Essentially what this means is that you need to add an NMR console, and that you need to add some coils and capacitors, variable capacitors, so that you have a tuned NMR circuit in combination with your EPR probe. In the picture, you see your instrument. You see also Sanjay, PhD student in my group. And what you see here, the box, that's our Q-band amplifier. It produces 50 watts. And with these 50 watts, we can generate an electron Rabi frequency of about 38 megahertz. So you see that we cannot fully match the on-resonance novel condition, but we're doing pretty good in terms of mutation frequency that we can generate. So all the experiments I'll show you are again done with the narrow line radical trital in DMP juice. Now, typically, before you actually start measuring, it's wise to do some analytical theory and also to do exploratory numerical simulations. The reason is that for all three of these sequences, you have choices to make in terms of pulse length, Rabi frequency, resonance offset, and for TPPM also the phase difference between the pulses. So it's good to do some quick numerical simulations to see how you set where you can expect your enhancement. And so that's what you see here in the top row, simulations for top DMP. On the x-axis, the microwave resonance offset. On the y-axis, you see nu1s, so the Rabi frequency or mutation frequency of the electron. So when we do our experiments, we typically set just one Rabi frequency, and then we measure what we call a field profile. So we vary the resonance offset, and we measure our proton NMR signal. So here in red means positive enhancement is expected. In blue means negative enhancement is expected. And you see that these simulations do a pretty good job at predicting the experiments and what are the good conditions to get an enhancement. The same here for the XIX experiment. You see that again, the experiments do match quite, or the simulations match quite nicely with the experiment. For TPPM, we did experiments at a higher electron Rabi frequency, 33 megahertz. And we also had to optimize the phase experimentally. But here also, the simulations did a good job in predicting the good DMP conditions that would give a high enhancement. Okay, so now I think you may want to know, okay, which sequence is now the best one? Which one gives me the highest enhancement? Now, before you can answer that question, there's actually several optimization steps that you need to do. So first of all, what we did for all three sequences is we scanned the full parameter space. So we explored all reasonable pulse length going from 4 to 64 nanoseconds. And for TPPM, we explored all reasonable, or we changed the phases in steps, we ran the simulations, and we looked for the good DMP conditions. We then tested them experimentally, and that's how we settled in the end for the TPPM sequence at this pulse length of 16 nanoseconds and a phase difference of 120 degrees as the best condition. We need to optimize the contact time, so that's how long do we apply our pulse sequence. We did here an attempt at, or we did also numerical simulations. And so taking into account also G anisotropy and relaxation. And you see here on the right, you see our experimental results, but you see that simulations here don't match that well. And in particular, what we know also from our analytical description of the pulse sequences, we know that the transfer is fast for TPPM, slightly slower for XIX, and then still slower for top DMP. But in the experiments, we saw that this doesn't quite work that way. And I'll come back to that at the very end of my talk. Okay, so what we also need to optimize is the repetition time. So how fast do we repeat the pulse sequence? As it turns out, the optimal repetition time depends strongly on the sequence. Top DMP, this is our experiments. Top DMP likes to go very fast. The faster, the better, it seems. XIX has an optimal repetition time of about 200 microseconds, whereas the TPPM sequence likes to go slow. The optimal repetition time is about a millisecond. Finally, what we also investigated is the dependence on the nutation frequency in the experiments. And so what we investigated is here for XIX and for top DMP. So you see here again, simulations. And at all the positions that the arrows point to, we did a little field profile. So we optimized the resonance offset. And there we optimized the repetition rate of the pulse sequence. And then we measured finally the enhancement. So we did this for both these sequences. And much to our surprise, and somewhat in contradiction with the simulations, we found that for top DMP, the higher nutation frequency, the higher your enhancement becomes. However, for XIX, we found that it doesn't really matter what your nutation frequency is. Already at a nutation frequency of 7 megahertz, the performance is pretty much optimal. The only thing that you'll notice is that there's a slight decrease in the build-up time of the bulk polarization. Okay, so now this work brings us together in a summarizing table for comparing the performance of XIX and top DMP and TPPM. Where we investigated top at 19 megahertz nutation frequency, and also with that much stronger microwave pulse of giving a nutation frequency of 40 megahertz. So that was a good day for the amplifier. Now there are some take-home messages from this. And the first one is that the scaling factor, so the preservation of the electron-proton dipolar coupling in the effective Hamiltonian, extremely correlates with the build-up time of the bulk. So if the rate of the transfer is faster, if the dipolar coupling is better preserved, this means that the build-up time is shorter. And this is something that you might also intuitively expect. What we found, though, is that the scaling factor, so the rate of this transfer, does not relate to the final enhancement that you can obtain. So final enhancements were fairly enhancement factors, so that's just measuring on-off. So they were pretty similar for XIX and top DNP. TPPM, though, did much better. But it seems that there are other factors in the pulse sequence that determine this final enhancement. Now, taking together enhancement factor and how fast you can get there, so build-up time of the bulk, we get to these final performance numbers, and we see that TPPM is clearly the best sequence. And what's important to note is that the average power that it consumes is not much more than for XIX and top DNP, just because though it requires a higher nutation frequency, and that's because the repetition time is so, the optimal repetition time is so very slow. A good number 2 is the XIX sequence in terms of its performance. The buildup is fast and the enhancement is also high. And here we note that this performance can pretty much already be accomplished at a nutation frequency of 7 megahertz. So even if you have low power available XIX, or if you have low power available XIX, the XIX sequence is probably your best bet. Okay, so these results and also the results obtained by others, they were very helpful actually, because they made it possible for the teams of John Jelonek and Chagri Ulesoy. So they are microwave engineers working at KIT, Karlsruhe Institute of Technology, to get funding to build a 263 gigahertz high power amplifier system. That would eventually serve as a source for post-MAS DNP at 400 megahertz or 9.4 Tesla. And here you see a picture of design of the amplifier system as they are constructing it at the moment. So they start with a solid state source where they aim at a power of about 1 watt. And this is then fed into a quasi-optical feed system going to an amplifier, which should eventually produce a 30 dB gain. That would mean then eventually they would be producing a kilowatt, which should be, well, a substantial power and should make it possible to do pulse DNP at this high fielding frequency. Now, the design that they chose is actually quite different from anything that exists at the moment. So for their solid state source, they're taking a very different approach than, for example, what Virginia Diodes is doing at the moment, where they up-converting from microwave radiation that's first generated at lower fields and frequencies. So they start immediately at 263 gigahertz, but then still to generate the high power, they combine an array of small sources into one. And that's how they aim to get to the 1 watt. And at the moment, they're not there yet, but the first results are pretty promising. For the amplifier, the idea is to use a helical interaction structure. And this is also new at this high frequency. There are some precedents at lower frequencies, but an interaction structure that can amplify microwaves at this small wavelength and high frequency has not yet been shown. Okay, so on our side, there have also been some new developments. And so what's been bothering me about the simulations and the analytical description that we've been doing so far is that we're only considering the single transfer. So we're just considering one transfer from electron to the proton space. So this is what our modeling was based on, both the analytical modeling and also the numerical simulations. But of course, as you know, this is not the whole DNP process. It's an important step. So it can be a bottleneck, but there's clearly more going on. And so the first thing that we would like to add to this simulation is the repeated transfer, because after all, when we build up the bulk polarization, we have to do this transfer typically thousands of times to get to this. Well, you've seen the pulse DNP scheme by now. Now, this is computationally costly to do because this means that we would need to simulate or model tens of thousands of propagations. So it's not so easy to do. What this would look like then, and here just giving you an example of this repeated explicit propagation here for the novel pulse sequence at X-band. So this is a simulation of just one transfer. So this is during the contact time of the novel pulse sequence. Here is a simulation where I included 4 protons and 1 electron spin in my spin system. And so you see here these oscillations that remain after the powder averaging, but you see that the transfer of magnetization is happening first faster for the close by proton, and then at a slower pace for the other protons which were somewhat further away. So this is what happens during one transfer. So now let's say I set my contact time to 2 microseconds. So I turn my microwaves off. And now I'm going to simulate the repeating of this transfer, let's say 8 times. So you see here this simulation, again, for these 4 protons. So the spike here comes from this initial oscillation. So I stop the microwaves after 2 microseconds. And then I just let the system evolve without any microwave irradiation. That you see here. I do another transfer, let the system sit. I let the electron spins relax. I do another transfer and so on. And so now you see that with each transfer, you gradually pump more magnetization into the spin system. If I repeat all of this 512 times, this is the curve you get. And so now note the scale change here. So I went here from microseconds to milliseconds to seconds. And what you then see is that, and this is not unexpected, is that in the end, you reach something that you can consider a steady state. Or more correctly, it's actually a steady orbit, because with each time we pump the magnetization in the transfer, we still change the system, but it's now recurring every time to a similar state. So the state still changes, but periodically it comes back to the same. It comes back to the same state. So this I'm going to call that in the next slides. I'm going to call that a steady state that we are reaching. So let's look a bit more closely at the code that one would use to simulate this explicit propagation. And in this case, this is now code as it would be written in Spinach, in the magnetic resonance simulation library Spinach, which we used for all, or we use the kernel for all our DMP simulations. And here for the XIX sequence. And we're doing here the simulation in Liouville space. So remember, the propagation in Liouville space looks a little bit different from what I showed you earlier. That was propagation in Hilbert space. Or actually, it looks much simpler now. So our state of our system is no longer described by a matrix, but now actually all those matrix elements are placed in a vector. So that is what's meant here by rho. And this is now our propagator. So it's e to the power minus L. L is now our Liouvillean times t, and that gives me the state of my spin system at time t. So actually the situation now looks, the propagation now looks simpler, and actually using or doing simulations in Liouville space numerically has a lot of advantages over doing them in Hilbert space, and you'll see another one of those in just a moment. Okay, so this is now the core of the post program for XIX DNP. So the first thing we do is we compute the propagator for one block of XIX DNP. So we call the Spinach function propagator, and actually we call it here first to describe, well, it actually takes the properties of our spin system. It takes the pulse duration, in this case XIX, maybe the length is 48 nanoseconds, for example. And here we take the Liouvillean of that considers the X pulse. So here we've also made sure that we added the microwave irradiation along the X direction. And then we multiply with that the propagator for the minus X pulse. So here in L2, I've added my microwave irradiation along the minus X direction. So this is now the propagator for one block of XIX DNP. Now I'm going to not just apply one block, but I'm going to apply in total 128 blocks. And so I need to calculate my propagator for the entire sequence. And I can simply do that by multiplying 7 times p times p. So 2 to the power of 7 is 128. So now I have my propagator for 128 XIX blocks. Finally, to get a total propagator of my DNP pulse sequence plus the delay. So this is now essentially the block that I'm every time repeating when I'm doing the DNP cycles in pulse DNP. I just need to add the propagator for the delay. So here I wrote that the Liouvillean as L0, so I think there's no microwave irradiation at this time. So this gets me my final propagator P. So this propagator, I multiply it with P as I calculated that in the previous line of code. And so now what I'm going to do is I'm going to propagate my spin system until I reach this steady state. So the steady state, I'm going to go through this while loop, and I'm going to keep going as long as the difference between the new state of my spin system compared to the previous state of my spin system is larger than some number that I can adjust to until my system essentially converges and I can adjust in my simulation. So after many post-DNP cycles, the system will reach a steady state where the state of my spin system no longer changes, even though I continue to apply my propagator. I've then reached the steady state, and I can now read out, again, as I usually do, I can read out the expectation value of IZ, so my longitudinal magnetization of my nuclear spin. Now this code, and especially this, the way that we check if we've reached the steady state, suggests a shortcut to go to the steady state. So we know the propagator, P, that describes the DNP pulse sequence, followed by the recycle relay. We know that, we can calculate that. Now, once we've reached the steady state, P no longer changes the state of the spin system. So I apply it to rho infinity, so that's my steady state. But it will have no effect. So I can subtract here again the state of our spin system. In the steady state, I will get 0. And this now suggests that we can find rho infinity. We can find rho infinity in another way. We can use it, we can find it just by solving this equation. And a numerical, or a smart way to do that is to use Newton's root finding method. So for Newton's root finding method, also known as Newton-Raphson's method, you need to go back to your undergraduate course in calculus, because I'm pretty sure that you learned it there. So here's a figure that could have taken from that course. So what you have some reasonably well-behaved function f, and you want to find the roots of that function. And so what you do is you start with a guess for the root, maybe call it x0. And so you calculate now at f of x0, you calculate the derivative of fx. That gives you this tangent line, and then you search for where this tangent line intersects the x-axis. And I'm going to call that point x1, and I'm going to repeat the process. So I'm going to calculate the derivative of f at x1 to get another tangent line. And again, I'm going to search for where that tangent line intersects the x-axis. I'm going to call that x2. And as you see nicely in this figure, for a function that's reasonably well behaved, this gets me in just a few iterations pretty quickly to what's called x star here, the actual root. So where the function actually intersects 0. And so as it turns out, we can use this idea quite nicely to find the state of our spin system in the steady state. And so this has been competently implemented by Yakupov, who helped us a lot here in this project. This required implementation. The actual implementation requires some fancy footwork, but it's now implemented in the function steady and is now available on GitHub in the Spinach library. So meanwhile, but we realized that how nicely this was working. My postdoc, Shiba, has been using this to do better simulations of post-DNP. And as you see, the results are really very nice. So what I've so far been sweeping under the rug is that when we do with a single transfer and we simulate our field profile, I never show the simulated field profiles because they don't, well, they're okay. They give us an impression of where we need to go in the experiment to get the best conditions. But when you compare this single transfer simulation to the experiment, you see that it doesn't match quite well. This feature in the center is way too strong. The peaks are too pointy. We don't simulate what's going on here. There's intensity here. We don't reproduce that. And now when we go to the steady state, you see immediately that things get a lot better. The shapes of the peaks get much, much nicer with the experiment. The intensity of this feature is much reduced. We see intensity here in between the peaks. So really, it makes a big difference. It helps a lot to simulate in the steady state. What we've done in addition is we do ensemble averaging. So we've been averaging over the distance between the electron and the proton. And I should say that in these simulations, we're just considering one electron and one proton. But now we're essentially smearing out this proton over a thick shell and taking a radius from 3.5 to 20 angstrom. This improves the match with the experiment further. And we're also including B1, so microwave field strength inhomogeneity, in this case, going from 10 to 20 megahertz. And now you see that also this feature in the center really starts to match the experiment very well. So what's not so easy to find proper parameters to do the simulation, in particular the relaxation parameters. That was not so easy. So we can measure the electronic relaxation parameters. This in the experiment, T1e and the 2T2e, we have some reasonable values for that. But what we don't know, or what's difficult to measure, is are the relaxation properties of the nuclei close to the paramagnetic center. So what we then did is we actually went back, we consulted some old literature, consulted Abraham and Goldman, and then we found an expression for T1 where we make it orientation and distance dependent, leading up to the bulk value, which we can again measure, of 52 seconds. So essentially, due to the dipole-dipole interaction between the electron and the proton spins, as they get closer, the T1 will become shorter. And of course, this is then also orientation dependent. So we included that into our model. For the T2n, which we were struggling what value to put, we just put a bulk value that we estimated from the decay of our proton echo, which was about 20 microseconds or thereabout. So we assume here that the T2n does not change when we get close to the electron paramagnetic center. So with this set of parameters, we were able to simulate the experimental field profiles very well, but we could also simulate very nicely the contact curves. So here you see our previous attempt at the simulation, but this was just a single transfer. And here you see the experiments, which I've also shown you already before. And here you see now the simulations in the steady state. And here we don't have that much data points, but apart from that, you see that we now match the experiments much better. And in particular, what you see is that we now reproduce the experimental behavior in terms of how long does it take to get the transfer done. And this unexpected behavior, the fast transfer of XIX being almost or being even faster than TPPM that we could not get in our initial simulation. And so what's probably happening here is that when you repeat your transfer many times, that actual trajectory that the spins undergo under the influence of the XIX sequence is no longer the trajectory that we initially analyzed, that we calculated and when we did all the math. It probably settles on some other equilibrium trajectory, which happens to lead to a larger scaling factor and therefore a faster transfer. And so with the single transfer simulation, we could not simulate that, but in the steady state, we can simulate that quite nicely. So finally, we could now simulate the optimization of the repetition time, which was previously, of course, not possible at all. So you see the experiments, again, top XIX and TPPM DNP, with TPPM needing the very slow transfer. And here you see the simulations with the parameters, the same parameters that we used throughout. And you see that these simulations do a pretty good job at predicting also this optimization of the repetition time for both, for all three sequences. Okay, so this brings me to my summary. So there are DNP sequences beyond novel. So actually there are probably many more out there, but a family that we have now thoroughly investigated, that's now established, is the family of top XIX, TPPM, and beam, which all follow this high field friendly matching condition, which is not to say that high peak power will still be necessary in order to get pulse DNP to work. What I think is crucial in the further development is better modeling and experimental investigation. And I think they really need to go hand in hand in order for us to develop this method further. Construction of microwave sources for high field pulse DNP is in progress, which I think is a really great thing that's happening. And so for recently, the new results I've shown you, we can now simulate pulse DNP in the steady state. And as you've seen, this leads to much better agreement with the experiments. And so it's a valuable new tool for testing pulse sequences. And as a final bullet point, the ultimate DNP sequence has not yet been found. There are other sequences out there, maybe also dedicated to answering different questions or different types of DNP experiments. And so we just have to design them, test them, and use them. This brings me to my acknowledgement slide. The work that I've shown you about the XIX and TPPM sequence, that was done with my former postdoc, who is now with Asif at NYU Abu Dhabi. So with him, I developed the theory. Sanjay did most of the experiments that I've shown you, and Shiba has now been working very hard on improving the simulation methods. Also in my group is Charlotte. She doesn't work on DNP, but she's quite good at asking relevant questions during group meetings. So yeah, she's also made her contributions to this project. Ilya has been very helpful in answering all our questions whenever we wanted to simulate something in spinach, and also been instrumental in developing the steady state simulations. These are the microwave engineers that we've befriended, so they've been. I've not been able to show everything that we've done with them, unfortunately. The funding at the bottom, and thank you for your attention.
Thank you very much for that excellent talk, and for the detailed explanation of the different mechanisms and the way that simulations were done, and the things to consider when you're designing these pulse sequences, and also how you go about designing a new sequence like this. For people in the audience, if you have questions, please enter them into the Q&A, and we can take a few minutes to try to answer some questions. Maybe I'll start by asking a question, which is that you showed DNP bulk polarization buildup times and enhancements for these pulse sequences, and I'm just wondering how they compared under the conditions that you were using. How do those conditions compare to, or how do those sequences compare to off-resonance novel or just CW-DNP?
Yeah, that's a very good question. So we didn't actually compare it to at Q-band. We didn't compare it to novel. Well, first we can't reach that condition quite yet, and so the off-resonance novel we haven't tested it. But I would suspect that off-resonance novel, if we can do it, that it's pretty good, that it will be comparable to the TPPM sequence as well. Yeah, if we can reach the condition, yes. Yeah, so we haven't experimentally done it, but it's something that we should do, probably. Yeah, we should do. It will be, I think it will be pretty similar. Yeah. Yeah. Okay. The build-up times, yes. Yes.
So what are the things that you have to consider when you're selecting a polarizing agent for a pulse DNP experiment? And are those different than what you might have to consider? I imagine they are, but if you could talk about what the things you need to consider are.
Well, so we chose tritol because it was known that it also works nicely for the solid effect. It has a fairly narrow line, so yeah, this makes it also easier to describe, because we can just treat it essentially as another nucleus, and we could copy the theory, and so this made it easy for us. What probably helps in making tritol such a good polarizing agent, and that leads to the high enhancements, is the radical itself has been designed to keep the protons somewhat far away from the unpaired spin density, so they all sit sort of in a shell at about 5 angstrom. And so this probably means that they're not protons that you cannot dynamically polarize, because they would sit inside the so-called spin diffusion barrier. Probably most of them sit just in the right place. And then the fact that there are many also helps to speed up the rate of the transfer. So I would think it's difficult to get to design something that's much better than tritol, because it's already pretty much ideal. However, yeah, going to higher fields and frequencies, it does have a little bit of G anisotropy, so it does become broader. So that is, yeah, something where one could maybe do better. The alternative would be to look at BDPA, but yeah, BDPA, then yeah, it's just more difficult also to keep it stable and polystyrene. So that, yeah, something one could do. We did run tests also with nitroxide radicals, where we see that it works, but not nearly as well as with tritol. I even tried it at some point with gadolinium DOTA. You probably know it also has this very narrow resonance condition, and that works as well. You just need to, this was just the first test. You need to go to fairly low temperatures to get it to work properly. So it's just a more difficult experiment. But I think it's definitely worth to go into that direction more, looking also what can you do with transition metals or DNF elements, the lanthanides also. Yeah, because those are also polarizing agents that you can, under conditions where you can't use an organic radical, those are the ones you may want to use, and those are also the ones you cannot really excite very efficiently with CW-DNP. So that's definitely the direction we're thinking about to develop pulse sequences, especially for these polarizing agents.
That's great. So we have a question from the audience. In your steady state simulations, can we say that T1 relaxation of nucleus of the nuclear spins simulated the spread of magnetization into the bulk proton bath. If I'm reading that right.
Yeah, it's in the chat. Let me. Is it, or is it? Sorry, can you repeat the question? The question is about a T1 that we use in the steady state simulations.
Yes.
And so, what is the question?
I'll read it to you. In your steady state simulations, can we say that T1 relaxation of nucleus I think it's just a question about how the T1 relaxation is related to the spread of the bulk proton polarization in the bath.
Yeah, we're not explicitly simulating that at the moment, right? Because we just take we have one electron and one proton. But as it turns out, that already gets you you can already simulate a lot of the features that you see first of all in your field profile and also in the behavior also in the behavior in terms of repetition time and contact times. So what we do see is that the values that you pick have a big effect actually. So for the T1 in particular, so if you pick your T1 too short, you see that your field profiles start to look essentially like in the single transfer again. And also if you make your T2 too short or you manipulate that, then you also see that you get strange behavior. But we think that this is what we've done right now is a reasonable way of doing it because we can assimilate both the field profiles and the contact curves and also the optimization of these repetition times. We can simulate that with one set of parameters. And so I think it's also not unreasonable to assume that the T1 then does get shorter when you come closer to the paramagnetic center. And we also see that this improves our match with the experiments as well. For the T2, this 20 microseconds where we just stick to the bulk value, that's also not unreasonable because, what we think is that in trital where these protons are relatively far away from the unpaired electron, it's probably the bulk or the proton flip-flops, the bulk mechanism that dominate the T2, that dominate that relaxation mechanism. And they will also determine, for example, here, how fast can you repeat your transfer. And so that's why we think it's not unreasonable to stick to the bulk and not change that value when we get closer to the paramagnetic center. I hope that answers the question sufficiently.
I think it did, but I have a follow-up question. So this goes to the simulations you showed of multiple spin transfers, and it looked like in the slide that you showed where you were considering four spins, most of the transfer is happening during the pulses, I guess, right? At least, especially at the early times. So does that mean that designing sequences where you want to make the fastest bulk polarization buildup time that you can get, does that mean that it will be important to explicitly consider these multiple transfer effects when you're designing those sequences?
Yes. So this is what we also see, that the build-up time of if your sequence allows it, so it depends on the sequence, but if your sequence allows it, that your bulk build-up time becomes faster when you repeat the sequence faster, which is also what you're expecting, right? If you're more vigorously pumping, that you will reach that high enhancement, you will reach it faster. So you just create the contact between the electron and the protons more often, faster, and that will speed up your bulk. Yeah. So there's probably some optimum that's somewhere, and it depends on the sequence that you're using. But that is what we see.
See, do we have any more? We don't have any more questions right now from the chat, but I have one more question I wanted to ask, which was, so the microwave source that you showed, the gyro TWT, is that is that right? So that sounds very interesting, and I just sort of wanted to ask about if you could say a little bit more about that source, and also just talk about what are the other leading candidates for high frequency microwave sources that could be used for these DNP.
I am not sure if there are many more other leading candidates. I mean, there is, of course, the structure by that was developed also in the Temkin lab, you probably know, where they had a photonic bandgap was at 250 gigahertz. photonic bandgap interaction structure. So I think when it comes to these gyro amplifiers, it really comes down to, okay, what kind of interaction structure do you design? How easily can you manufacture it? I think this is very important. And yeah, then how stable is it in the use? But there are not that many. There are not many people who can do this, who have the know-how and also to design and build these things. So yeah, this is, I mean, it's definitely different from what other people have done. How it's going to compare, and I cannot say. I think it's also a matter of trying it out in practice, which design strategy works the best. Can you come up with something maybe that's also scalable? So yeah, we'll have to see. It's fairly new field to do these things. So yeah,
it's an exciting area of research, and hopefully there's more work done.
It's very interesting. Yeah.
So we have one more question. This was entered in the Q&A from Marcel, who asks, how does the enhancement change with T1E? And he says, I was just wondering about possibly using this at higher temperatures.
Yeah, so we can simulate that now. We're now just at the point where we can start to simulate. So if the T1E definitely also plays a role in what is your optimal repetition time. So you can repeat your sequence faster when you go, or you will have to repeat your sequence faster when the T1E is shorter. Yes, that's definitely how it would work. Whether you can then always reach the same enhancement, this is, I think, something that needs to be explored. I think it's something we need to explore further, what you can do. So what we've done with the novel sequence, for example, is and this applies to some extent to the TPPM sequence as well. I have to select this. Is that with the TPPM sequence, you really move your magnetization all over the place. And so it's not so strange that you then have to wait a long time before everything settles back to thermal equilibrium. And the same applies also for novel, where you essentially excite on resonance, and then you also will have the magnetization go far away and largely into the XY plane from equilibrium. And so this is very different from what you see for top and XIX, where you stay fairly close to the Z-axis. And therefore, it makes sense that you can repeat those sequences faster than TPPM DNP. Now, what we've done or tried in this to solve this problem for novel is that we said, okay, instead of just applying the 90-degree phase change alone, we apply a flip back pulse at the end of the novel sequence, so that we help the spins already to get back to the Z-axis. And that helped, that got us higher enhancements, and also it allowed us to work at a faster repetition time. So it's an interplay between the T1E and the sequence that you're using. How that's going to play, I think it needs to be investigated, I would say. I have no definitive answer of what will be the consequences and what one can do at higher or lower temperatures. It's not really been done, so I don't know.